Recording has started, so welcome to a new week. It's a 4-day week. Come back from 3-day Labor Day weekend. You guys have a good weekend? Yeah. All right, good deal. All right, so here's the tentative schedule for this week. Our main focus today is going to be AP Classroom multiple choice questions. A couple of you guys didn't turn that in, so leave that up for a while, and then actually I have to reopen that, so I will do that soon, and then you guys can put your answers and get that. We'll look at those. Now, before we get to there, talk about some other things. So, got a lot for you guys tomorrow. I'm going to leave this a bit open-ended, but I do want to show you guys some of the equipment today so you have an idea when you come to class tomorrow what it's going to look like. I'm going to get you guys a take-home quiz on Thursday. Right, so a few more days of doing this kinematic motion. Then now this will be a take-home quiz that will be due Monday. So if you want to do it Thursday night, bring it in Friday and have the weekend, then you can do that. If you need a few days to do it, it's a pretty challenging quiz. Take it at that. And then this college physics questions. Okay, you guys remember chapter 3? Looks like this. Okay, you guys have had this page a long time. Keep trying to get to it. So I think Thursday is going to be our day for those. Okay. And then Friday, I'd like to do an FRQ with you guys. We'll see if we have time to do that. Okay. You guys remember also that I'm picking up your guys' chapter 3 homework this Friday. And what I assigned to you guys was, remember you have a couple pages. You guys have this chapter 3 book problems, all my favorite book problems from chapter 3. I also have all the solutions written out. Okay. And then, you guys remember I also gave you guys the page with boxes, a bunch of projectile questions. Okay. And what I told you guys to do was just to choose 8 between these two collectively. That seemed like a good idea at the time, like, hey, here's like 40 awesome questions, pick 8. In retrospect, I think that was a bit more confusing than I'd intended it to be, so I think in the future I'll probably pick specific problems. So, it's worth a try. I don't think it was the best way to design stuff, but anyway, that's what I'm going to pick up by Friday. So, any questions on that so far? All right, so you guys had, some of you guys made flip books, and some of you guys made some really awesome flip books. And it said if you turn one in, then I'd want to show it. So let's take a look at these. I've got, looks like a flying saucer going past Earth. Yeah, Fiend. That's about the fiend of all fiends.
Good job, John.
Got this guy. Oh, yeah.
John's such a master.
That blobfish, that shark. Man, this one's action packed. We got, jetpack penguin. That's out of there.
I love jetpack.
Nice. We got, this one's called Hiroshima.
Oh.
All right.
Is that the end?
That was the end. Wait a minute. I know I had a.
Is there a part 2?
I'm looking for a part. I think I found a part 2.
Oh no. Oh no. Okay. That's
The
end. Let's go.
Can someone accidentally
and then I get every frame. Words scroll out. It's pretty cool. Projectile motion. Begin.
So proud.
And this one's really cool, though. It's kind of hard to flip, but maybe I'll do a frame by frame on this one. Watch a frame by frame analysis like the Zapruder film. The splash. Oh yeah. Alright, yeah, so you guys did a really awesome job on this. Got some points. Right. Now, aside for tomorrow's lab, I'm actually going to throw one of a couple of questions at you guys, but it's going to involve this equipment. It's going to involve a launcher and little plastic ball. So there's different questions you could go with this. You could figure out what is the launch speed, like how fast is it blasting, which, that might look a lot like the starter question, couldn't it? Huh. Right. Another really good projectile question is, what is the optimal angle to send it the furthest distance? So that would involve, do you guys see like a protractor right here? And the string coming down with this clip? Right? Do you think as you adjust this, the string will naturally hang through how many degrees it is from the vertical? Right? Yeah, so you can do that, right? Right. Hey, look at this. It's like a spring ball. Listen real close. You guys see that click? Right. That means this thing is locked and loaded and ready to fire. Oh yeah, look at that. That is gonna be a dangerous lab, but not as dangerous as, listen closer. Click. Click. Oh, it's a double click. Oh, double blast. Ooh. All right, you guys think we're done with that? You are wrong. This is what 3 clicks. Oh, fire back at me, bouncing off the wall. There's 3. There's 3 clicks. All right, let's hop into this the starter question. Hey, a lot like that setup, possibly. Now tomorrow I'll take you guys outside, and this could be one of your setups. Right? You could also have a different setup, but it might be this. You can find a good height, and you just launch it straight horizontal and see where does it land. Did anybody figure out the answer to this question? What's an expression for the speed just based on those two? Right, you've got a vertical height and a horizontal distance. There's also, of course, a gravity field you're in. Like that matters too, right? The gravity field. Right. Who knows the answer? How fast? Right. Well, how about this? Wouldn't the blast speed just be how far it goes horizontally divided by however much time it took to get there? Right? Right? So distance divided by time, something like that? That would make sense, right? Right. And the distance, okay, well, that's easy because that's just measurable with the meter stick. But wow, what about the time? Hey, isn't the time constrained by how long it's been falling for? Right? So we could use this to figure out the falling time, and then take that falling time, which is some function of the falling height, right? And take this distance and divide by that. Wouldn't that just be the answer? Right? That makes sense, right? Okay. In fact, here's how I'm going to solve this. I'll do this. Here's the honors version. I gave them numbers. So I'll do it side by side. Okay. We'll solve with numbers and solve in terms of variables. Wait, do I want to do, I think I want to do the other way around. Let's put variables on the left, numbers on the right. Yeah, that makes more sense. Okay. So the process was, remember, we're going to start by getting the time, and that's based on the falling height. Right? It also helps that this was launched horizontally, made it was at an angle. You can still solve it, it's be a bit more complicated. Okay. So wouldn't it be true that the height it falls just boils down to 1/2 gt squared? Because it was aimed horizontal. Right? I could say v naught t plus that, but if this is all strictly in the vertical direction, see the initial speed of the ball vertically, which is 0, it's not going up or down. Okay. That's a good general setup. Okay. I'd like to solve for time. Okay. And in the honors version, I'd be plugging in some numbers along the way. So I might say like 7 meters. You guys see that 7 meter height drop? So 1/2, let's call this about 10 meters per second squared for some time squared. Do that, right? Okay. Now, since you guys are doing variables, so you multiply the 2, divide the g down. So 2h on g could be t squared. Square root both sides. The t is the square root of 2h on g. Right? When you guys wrote that step, did you guys make sure that the square root bar extends over the entire fraction expression? Yeah. Throw some parentheses for good measure. Okay. What about on the honor side? Multiply by 2, divide by 10. So that'll give you 2 times 7 meters, divided by 10 meters per second squared. And take the square root of all that. That would be your time. Let's get a number for it while we're at it. What is the square root of 2 by 7 over 10? Okay. It says 1.18 seconds. No, 1.183 seconds. That's way too much precision, but it's a middle step. It's not the final answer. So it's usually good practice to save your rounding for the end if you do something like this. Okay. Hey, how far on Earth does anything fall in 1 second? Yeah, you guys remember 5 meters? Right? You guys remember here's ball falling off the cliff, this poster over here? Right? 1 second. It picks up to 10 meters per second, but it only fell 5 meters. That's 1/2 AT squared, right? You guys remember that? And hey, look at this. So to fall 7 meters, it'd probably be a little bit more than 1 second, which exactly lines with that, doesn't it? Okay. Right, so that's just a middle step, though. I really want to know, what is this last speed? Okay. And all this stuff was vertical information. Okay. This was all vertical. This was all vertical. Okay. Let's switch over to a horizontal analysis. Horizontal. Okay. So that's how the rest of this is going to finish out. Horizontal. That's for anything else I write. It's going to be referring to what it's doing left, right. Okay. You could start with x equals vt, with the subscript x, or if you want to, you could just go straight to vx equals x over t. You could just do that, right? You do that over here. How fast is it going? Well, how far did it go? How much time did it take? Right? Let's do the honors version first. Here's how far I said the honors version went. Let's say 5.5 meters. Let's plug that number in. So it'd be 5.5 meters. It took 1.183 seconds to do that. Get an answer. It is 5.5 or 1.183. Looking at 4.65 meters per second. Okay. That's if you have specifically these numbers to work with. Okay. But what about in terms of variables? Hey, couldn't I take this whole expression for time right here? Go, pop it in right here, just like that. So now we can get this blast speed in terms of how far did it go, and how high a ledge did it drop off, and the gravity. Like that. Now, that right there could work perfectly well. If AP asked you this question, they would accept that for full credit. But there is one more way you could clean this up. I do see a fraction within a fraction. You can take the bottom fraction and flip and multiply it. Get the blast speed is equal to x multiplied by square root of g on 2h. Wouldn't that be true? Okay. And that's the answer. That's your guys' AP answer. Okay. Now you have an expression for how fast it's going as a function of how far did it land and what's the height, and also what planet. Let's do the final check. I'm going to take the given numbers, plug them into this expression, and see if it still gives me 4.65 meters per second. It should, right? So I said it went 5.5 meters out from the base. That was that was the honors distance. Okay. Multiplied by the square root. Did gravity 10 meters per second squared divided by open parenthesis 2 times h, 2 times, and I had 7 meter height. That is 4.65. It's the same thing. Okay. You guys good? Any questions so far? All right, so that was a nice little warm up. I think we did something really similar to this last week too, so that should be a good review. On this side. All right. You guys ready for AP Classroom? AP Classroom?
Yep.